So this is basically a video response to Dave Murphy's 12 questions to Neil deGrasse Tyson about the flat Earth. First, I want to say, at the beginning of this video, he claims that everything in science is just a theory, and that nothing can be proven or anything like that. It's actually wrong. So, for example, take gravity. A lot of people say that gravity is just a theory. Well, gravity isn't just a theory. Gravity is actually a fact. The fact that things fall down whenever you drop it on planet Earth, that's what we call gravity. We call the effect of things falling gravity. The theory is Einstein's theory of gravity and Isaac Newton's laws of gravitation. Those are the theories explaining how gravity works. But the observation of gravity is no theory. Same thing with the Earth. The Earth being a sphere, for various reasons, isn't a theory, it's a fact. Now, why the Earth is a sphere and stuff like that, those are the theories. Anyway, let's begin. So, his first question is, why is there land at the equator? So he says that, well, the Earth being a sphere, sorry, my drawing is terrible. The Earth being a sphere and it's spinning around at 1,000 miles per hour, right? And so there shouldn't be land at the equator because water is much lighter than land and much easier to move, which is true. Therefore, there shouldn't be any land at the equator. Well, that's actually incorrect. When the Earth first formed, it was not just some hunk of rock, and it didn't have much water on its surface. It actually was a molten ball, right? A lot of primordial material all collided together and melted into this sphere. And so this sphere was basically a sphere of molten rock, and it was spinning at a certain rate, and that actually causes the Earth to be slightly oblate. Very slightly, but slightly. And there's no way there's going to be liquid water on the surface. So eventually the Earth, over billions of years, would cool down into rocks and stuff like that, and the water would come later. I mean, probably brought on by comets or whatever, but when the Earth actually cooled down enough, then water would rain down later. So the high places would already not have large, they have a few bodies of water in them, but they wouldn't have, water filling them up. So they'd be higher than the actual water level. And the low places would be filled with ocean water. And so you have the separation of continental crust and oceanic crust and stuff like that. So in reality, there should be land at the equator and water at the equator, because there is. In reality, the centrifugal force from the spinning globe is actually very small. And the gravitational force is actually much larger, and that keeps the water stuck to our planet. Alright, question 2 says, can I see the curvature or not? So basically, what he's saying is, if you can see enough curvature to hide a ship, the ship actually disappears over the horizon as it gets far away enough because the Earth is curved. But why is it that, so actually a little diagram he was drawing was that, say you're here on the shoreline. I do not draw well, obviously. And you can see, let's say, as he says in the video, 5 miles out. And that 5 miles is enough to actually hide a ship so that you cannot see it anymore. But across here, you can see 10 miles in either direction. So why can't you see enough curvature across 10 miles to hide the ship? Well, this is basically a misunderstanding of geometry, right? So, let's say this is 5 miles, right? How much drop do you need to actually hide a ship? Well, it depends on the height of the ship, but let's say that over 5 miles, I'm not sure, I think that the drop may be, let's just say 10 feet, just for argument's sake. That's reasonable. Let's say you get a 10-foot drop of curvature over 5 miles on the Earth. Right? So when you're looking straight ahead, if the ship is 20 feet high, then 10 feet of that ship is going to be hidden below the horizon, correct? However, when you're looking across, you're not going to see that curvature very well. And the reason is because when you're looking straight, the 10 feet matters because the ship has an absolute height. However, when you're looking across, your across view is going to be the same, even from 10 miles. Let me redraw this on another paper. So let's say your drop across 10 miles, right, is going to be, say, 40 feet. So let's say you have 40 feet of drop across 10 miles. But what's the angle here? The amount of curvature you actually see when you're looking across the water, when you're looking across the ocean, depends on the angular difference, right? So what's the angle between 10 miles and 40 feet? Well, 10 miles, of course, is 52,800 feet. So your angle, call it theta, is actually, when the angle is actually small, there's something called a small angle approximation that says that the angle is basically the same as a tangent. Tangent being the ratio between this length, 40 feet, and this length being 10 miles. So the angle is basically is essentially the ratio 10 miles divided by, I'm sorry, that's wrong. It's 40 feet divided by 52,000 miles, right? That's your angle. So that's about, what, less than a tenth of a degree? Or not of a degree, of a radian. And so, okay, sorry, I misspoke there, but this is the angle. You multiply it by 180 divided by pi to get the number of degrees. And so that is about 0.04 degrees. So that's your angle. Your angle across your field of vision when you're looking across the ocean, you know, like when you're looking out to the sea, your field of view is only dropping by some 0.04 degrees or so. It's an incredibly small. So when you're looking across 10 miles, you're still seeing 40 feet of drop, but that 40 feet of drop across, in comparison to 10 miles, is incredibly tiny. So it's perfectly reasonable that when you're looking out to sea, you can see a ship dropping 40 feet, or I guess in the case of 5 miles, 10 feet below the horizon. It's perfectly reasonable that you'll see that 10-foot drop for a very tiny curvature, because it's, you know, it's 5 miles out in just a 10-foot drop. When you're looking across and you're looking across 10 miles, you're only getting a 40-foot drop, so that angle is just an incredibly tiny angle. So you're not going to see the curvature. So that's just a misunderstanding of geometry there. So question 3 asks, why have we never seen curved water? So he's saying that basically if the Earth is a sphere, then obviously it's going to bend the water around it, right, into a sphere. So he gave an example of some lake in Siberia, I believe, that across that many miles that the lake is, you should see a 20-foot hump at the center, right? Well, no, that's another misunderstanding. But before I actually go into why that isn't the case, I want to first say that you can see curved water. If you take a cup, say the cup is shaped like this, and I pour water into it, sure, it may be a little flat at the top, but on the sides, it actually is curved. Why? Because the cup itself is forcing the water to curve. You have any force, and you can easily force water to curve. If you blow on the surface of water, you know the water starts to curve because something is forcing it to curve. The only reason it locally does not curve is because the gravity is basically, if you imagine gravity, for example, let's say this is a ground. Imagine gravity field vectors as these arrows. Those arrows are basically parallel. So they're going to pull the water down the same amount everywhere, so it's going to be level. However, on a sphere, a curved surface, your gravity field is now basically curved. It's pointing in different directions. And so the water is going to be pushed in different directions across the earth, and so therefore you're going to get this curved water over the surface, right? Okay, so, but back to the question about the hump in the middle of the water. No, that will absolutely not happen. If you're on a sphere, right, you have to realize what a sphere is. What I'm drawing here really is a cross-section of the sphere, which is a circle, which by definition is simply a set of points equidistant from a fixed point. So this fixed point is going to be the center point of the Earth, right, with a certain radius. But that radius doesn't change. By definition of the sphere, the radius is exactly the same everywhere, almost. And so in order for you to see some sort of hump in the water like this, it would mean that the height of the water changes, which means that the radius actually changes, but that doesn't happen. Flat on a sphere simply means that the distance to the center of that sphere stays constant. That's what flat is. So there's no way you're going to see a 20-foot hump. It's going to stay flat across the curving sphere. So you're not going to see this hump. Instead, it's just going to stay like this. Right. Okay, so the last question is probably the most interesting one. How are we breathing right now? How is there no high pressure to low pressure movement on a sphere that has, air being held down by gravity? Now, this is actually the last question I'm going to answer on this video because it's going to be way too long to answer all 12 now. So I'll answer the other questions in other videos. Okay, so this is basically the diagram that he uses, where he's basically saying that you have a non-vacuum here right next to a vacuum of space. And so air is just going to rush out, right? Well, again, this is a misunderstanding of physics, essentially. So let me first answer one question he asks, which is basically if he takes some sort of container on the Earth, right, and he punctures the bottom so that there's a hole here, and he sucks out all the air, by the way. So this is a vacuum on the inside. There's a vacuum inside of this container, and you're on Earth. And what happens when you puncture the bottom? Well, air is just going to rush in here against the force of gravity. How is that possible? Well, realize that gravity at the surface of the Earth isn't just fighting against, that amount of air inside of this vacuum, right? That's rushing inside of this vacuum. Gravity is fighting against the air that's all the way up the atmosphere. So all of this air. So if you have some sort of column, right? You're over here on the Earth. This entire column of air is weighing down, being pulled down by gravity, and creating a pressure, a large pressure of about 14.6 or 0.7 pounds per square inch that is pushing into that chamber. So you basically have miles of atmosphere of weight pushing down, creating such a large pressure on the surface of the Earth that is pushing into this vacuum chamber. And the weight of the air that gravity is trying to fight against is basically a weight of air that's only a few feet in this container. Well, who do you think is going to win? Clearly the miles of atmosphere above are going to win. The only reason this air is pushing into this vacuum is because it's not just the weight of the air in the room, it's a weight of all the air of the atmosphere above you. So that's the reason for that. I hope that made sense. If not, I'll try to explain it again, if someone asks in the comments or something. Now, as for the question about this boundary condition that he's talking about, he's claiming that you have this atmosphere here that there's going to have to be a boundary condition where the force of gravity perfectly equals the pressure pushing outwards. Well, that's not actually true. You need to realize that it's not just some, it's not just like there's a whole bunch of air pressure in here and then it just goes straight from 14.7 pounds per square inch straight to zero once you get to the other side. There's a gradient. As a matter of fact, if I were to plot on a graph, say our x-axis is height and our y-axis was pressure of the air. This is what it would look like. It's an exponential decay. This isn't just some theory. This is experimental fact. You can go up to Mount Everest and actually see, or actually measure that the air pressure is significantly lower. You know, Mount Everest would be somewhere over here on this graph, where the pressure is actually about 1/3 of what it was before. And the higher up you go in the atmosphere, the lower this pressure gets. Why is that? Well, like I said before, the entire atmosphere is crushing down on the air below it. So say this is the Earth. You have a box here. So you can imagine you have this huge box, you know, that weighs a lot, pushing down on this other box. What do you think is going to happen to this one? Well, it's going to be compressed a lot. And that's why the air is so dense down here. But then when you move up, this next box here is going to have less atmosphere pressing down on it. So its density is going to be slightly less. And hence its pressure is going to be slightly less. And the higher you go up, the less air that's pushing down on the box of air below it. And so therefore the pressure just continuously decreases. And so once you get to an appreciable height up here, it just fizzles out to zero. There is no boundary condition necessary. Matter of fact, everywhere gravity is matching the pressure that's pushing outwards. That's why it's not moving. The pressure of the outward push of the atmosphere is equal to the gravitational pressure pulling in. That's why there's an air pressure in the first place. It's because of gravity. Gravity is what's causing the pressure. So you don't need any boundary condition because gravity is creating the pressure. So there's never going to be any issue with, you know, equilibrium. The last question he asks is basically, how is it that hot air can rise? I'm using an example of a helium balloon, but it's exactly the same, right? Helium is far less dense than the air around it, right? And so, like I said before, these columns of air are creating pressure, right? But pressure pushes in all directions, not just down. Because if it didn't push in all directions, then the air column would just start moving in different directions or something like that. The pressure has to be equal everywhere. There has to be pressure pushing the box from above, from the sides, from the bottom. You know, it's getting pushed everywhere. However, realize something. Realize that, let's say if I take this helium balloon, like I said, the higher you go up, the lower the pressure is, which means that on the top side of the helium balloon, you're going to have a certain pressure pushing it down, because the pressure adds up to being tangential to the surface. But on the bottom of the balloon, because the bottom of the balloon is slightly lower than the top of the balloon, that means that there's actually more air pushing down on the air around it, which means that the pressure, as I explained before, is slightly higher. Well, what happens here? Well, if you have a force going upward that's slightly larger than the force going down, then what's your net force? You have a net force upwards. This is called the buoyancy force. So you actually have a buoyancy force that's pushing the helium balloon upwards. So in other words, the reason why helium in hot air rises is because it's less dense. In other words, gravity is creating pressure that is creating a pressure differential that is actually pushing up on the helium balloon. And it actually pushes up on all objects, you and me, and everything gets pushed up. The difference is that something that, so the force that actually pushes up on this balloon is equal to the volume of air that is displaced. So that means that if this is a rock, for example, the rock being much denser than the air, the volume of air that is displacing, let's say it's 1 cubic meter, it's only displacing 1 cubic meter of air, but a cubic meter of air only weighs 1.2 kilograms. But a cubic meter of rock can weigh, depending on the type of rock, but it could weigh as much as 2,500 kilograms, right? So even though this rock has 1.2 kilograms of force pushing it up, because it weighs, because it weighs 2,500 kilograms, it's making a very small difference. However, the helium balloon, a cubic meter of helium weighs, I think it's 0.17 kilograms, something like that. So it weighs less. So the force of 1.2 kilograms pushing this helium balloon up is actually more than enough to push it up. And so it's actually going to rise. Same thing with hot air. When you have a column of hot air rising, or column of air that is heated, you have hot air here. Why is it rising? Well, the same principle, right? It has more force pushing it up than pushing it down, because the cooler, denser air around it is more dense. That means that the force it pushes the hot air up with is going to be larger than the force that gravity is trying to pull it down. And that is the reason why it rises. So that is my answer to your questions. I doubt Neil deGrasse Tyson is actually going to answer your questions, which is why I'm trying to do this. So I would appreciate if you actually respond and let me know what you think of my explanations. And if I need to elaborate on anything, then I will. All right. Thank you.